Okay, we're going to discuss today the probability model, and this book is the choice book. Jungun happened to have a copy, and I cover like a certain portion probability model. Some examples are really good, and then I'm going to switch to the Lishkov book to discuss about the safety factor. You hear the safety factor all the time. Then what's the relation with the reliability of a structure system? That's the issue. then then we're gonna get a good grip on the basic reliability, structure reliability analysis. Then after that, we're going to switch to, but you don't have to really running around to get, who is missing today? 1, 2, 3, 4, 5, 6, 7. Not everybody here. Move to Professor Du. Du's really one write-up of the one chapter. I'm going to send you a file. Then you can, it really is I mentioned to you, is a really best write-up on the first order reliability method. You can really program to compute the probability of the failure. So that's what we're going to do. So don't feel, oh, he doesn't cover. I didn't insist you buy the book, right? Did I? I didn't insist you buy the book, but 2 sets of copies are readily available. Higyu has it. This week, Higyu is out to Lisbon to present a paper out there. So, but if you just walk into Higyu's the desk, then there is 2 sets of the books. Then you can just pick it up, put the name. If you return before he come back on Tuesday next week, just take it then and use it, then come back. Okay. So probability model. Okay, probability model. Probability model. For the probability model, I'm going to discuss first the log normal distribution. So how many heard about the log normal distribution? Anybody? Arlene, you heard about the log normal distribution? Have you used it? Okay. A teacher said, here is the log normal distribution, then put that in the trash basket, and that's the end of it. But log normal distribution, I really wish you enjoy it. Otherwise, its knowledge is just useless unless you are really use it, put your heart in there, then it's useless. So log normal distribution is very straightforward if you look at carefully. But if you don't look at carefully, then it's not very good, you know. So you can really use it for example, for structure reliability problems, okay? Log normal distribution has a very close relation with the normal distribution. That's why it has a name, log normal distributions. So the relation is something like this. This is, we're going to discuss log I mentioned to you whether I say probability distribution function or a probability density function in general, I put that everything in one basket. You can say probability function or probability distribution, okay? So nothing too really offending you. Log normal distribution, I'm gonna, let's say X, capital X is a random variable. It's a random variable. And also, I'm going to say that X is equal to X1 times X2 times Xn. And all Xi, if I say Xi, this is also the random variable. Of course, X is a random variable. So I'm going to take the natural log for this random variable. If I say that is log X is equal to log X1 plus log X2 all the way through log Xn. If this or this term, any term here, if I say this follows the normal distribution, so which means it's really the log xi in general. I is equal to 1 through n, okay? If this follow this natural log xi is a random variable, then if this is the follow normal distribution, then this xi follow log normal distribution. It's kind of a definition. So remember here, this is then I'm gonna say this is the y, and this is natural log. I'm gonna say this is y1 plus y2 all the way through the yn. If yi follow the normal distribution, of course y follows what distribution? Normal distribution. So this follows the normal distributions, okay? Then what I can do here is simply y is equal to natural log x. So this follows normal, nothing to confuse. This follows the log normal distribution. So y follow the normal distribution. We all know about the probability model for normal distribution. So I can write right away the probability density function. So why random variable follow the normal distributions? Because this is like addition of all the normal random variable, then end product y, log y, also follow the normal distribution. So I depict, say y is natural log x. So you can readily write the probability density function of y. Okay? So I'm going to wake you up. Oh, I forgot to bring my name sheet, so I can't wake you up. So normal distribution, of course, is, you remember, I don't really ask you to memorize, no. Probability density function of y is e to the minus, this is y minus mu y square 2 sigma y square. Naturally, that's what that's called the normal, the density function or Gaussian density function. Here is for the y, the random variable. And now what I need is the expression for x. That's what the log normal distribution function. So I want to see really the x informations also, because x is random, the variable is right there. So over here, I'm going to rewrite this as x is equal to e to the y power, right? That's e to the y power. So we are really looking for probability density function of the x variable, which is what the log normal density function is. We know this relation between the y and x. Then we know the fy, and what would be the fx? What rule should I use it to get this expression using the y information? We know y, it follows normal distribution. You remember the change of variable? If you look at the book, other approaches also available, but change of variable is kind of the very easy way to use it. And quickly, just to review quickly, this is like we use a gx. We know this probability model, then I'm in the position to find the probability model of y, right? Then probability models, of course, so that we use a notation x is equal to, it's simply notation is this. Then we are looking for this guy. So fy, we are looking for we are looking for, in this case, we are looking for, the Fy is correct, isn't it? Is equal to, let me see, is equal to Fx, x, absolute dy dx, something like this. Do you remember this? Never remember? Who cares? I think this is kind of a correct, I hope. Over something like this. We derive using change of variable, then we got the expression for the Fy, knowing the Fx. So similar equations, we can use it. So I'm going to say over here, in this equation, this is what you are looking for. So I can say Fx, x is equal to Fy, y, dy. I think should check it out. This is check it out. This equation set again. We have done it about 2 weeks ago, 3 weeks ago. So if I cast this into our format, this is what I can say this. And dy dx, so you have to differentiate this guy here. So dy dx from here is equal to 1 over x. So I can rewrite this as fx, x is equal to y times 1 over, strictly speaking, you can say absolute 1 over x, okay? Now we know this already. So, which is right there as a normal probability density function. So then you can just rewrite as a 2 pi sigma y and 1 over x. X has to be always greater or equal to 0. For log normal distribution, is x is greater and equal to 0. But in general, you can say any range. So I can still put the x bar. X doesn't have to be greater, but that's really true. That's really true for the reality. And I have to write here is minus, this is y minus mu y square 2 sigma y square still. Okay, this has to be careful. So over here, we know you have to replace this y by natural log x. Okay. This mu y, mean of y is a constant. Sigma y is a constant. From now on, I'm going to slowly switch the capital letter of y to just for the subscript as a lowercase of y. When I type in subscript, the the capital letter of the subscript getting too large. So I'm going to switch, for the subscript to lowercase. That way can handle easily. So now question is, this is a constant, and this is a constant, and this is a constant, okay? Standard deviation of y, or variance of y, or the mean of y. The expression for all this model, I'm going to give you the probability model parameters. So if you are going to really drive it, my answer is, of course, yes, you can drive it. But whatever is available in the Wikipedia, for example, in the internet, you can always find, look at the table, pick out the parameter, then your destination is to really solve the probability model to apply to something like a structure reliability. But you can, of course, readily derive the parameter. So I give you one example, example 2.4. Did I ask you to go through example 2.4, right? So example 2.4, which will derive, you will derive sigma y square variance, or sigma y, or mu y. Over here, y is equal to natural log x. When I say derive it, don't just look at it. Actually, put your pencil down and derive it. Okay? And I didn't ask you to submit, but you are welcome to submit. There is a tricky point a little bit. I want to see whether you could follow that nicely or not. So I'm not demanding to hand in, but you are welcome to hand in. Then I can take a look at, make sure, no point whatsoever, make sure it's all correct derivation. Then after that, all the parameters, I don't want to demand to do it. Whenever you look at the table, handbook, Wikipedia is all out there. So no reason to let you suffer. You got lots of other better things to do. So, but if you have to, then what I can claim is you can be in the position to drive parameters very easily. Example 2.4, how many did it already? Or like to do this weekend, a long weekend. Do this weekend. Okay, this weekend, do that. Still weekend, go to sleep between 12 and 1. Get up at 7 o'clock in the morning. Another reason, bad reason is, you can survive like that. Go to sleep 5 a.m. in the morning. Then on the way to the dorm, he hit the tree. He hit the tree. He drove right up. Because he, on the way home, he kissed the tree. He just fall right in. But his waistline was hit, but he's okay now. So that's why I'm really saying do that. Then at 8 around, if you keep that kind of the bad habit, when you become someday, not far away, you will be age of 40. Believe it or not. then what happens is, around the age of 40, if you keep that bad habit, you can, even if you want to go to sleep around 10 o'clock or 11 o'clock, you just can't. That's called the 불면증. At around early 40, people got that bad disease. That's a disease. Very uncomfortable disease. Can't go to sleep, can't fall in sleep. Then set up the whole night. Then fall in sleep around 5 a.m. Then by the time he wake up, it's 11 o'clock, then he missed it to go to work. So to avoid all that, this is all the professors talk all this like this, but young professor, they don't, right? Please do. It's going to really help you. So example 2.4, if you haven't done, please do. This is this book, choice book, has very nice way to give you solution using that example problem set. So that's why some of you may say, Jesus, already solution is there. Why I have to do all over again? Why? That solution is not yours. It's a choice. So I want you to make yours. That way you can extend the experience better. 잔소리, okay. And so this equation set, this is the log normal density function of random variable x, but over here the mu y and also the sigma y, you need, that's parameter you have to estimate based on, we know the basic definitions and all that. I'll just provide the information right here because you promised me to go through example 2.4 and natural log sigma x mu x square plus 1 and mu y is equal to natural log mu x minus half of sigma y squared. Mu x is the random variable for x. You know the mu x, that's a given based on data fits and so on. And sigma y is over here. And sigma x is a basic information. Okay, you should know based on the data set to fit into the model. Mu x, you know. This is you know, this is you know, of course this is you know. Then what you need to compute is this quantity and that quantity. First you compute this, then you compute that, then sigma y, mu y, then after you compute, you can fit right here, you can fit right here, you can fit right here, then you can express the probability density function, log normal probability density function, like this. And I want you to use this log normal distribution, then go through as I shown in the biweekly project. To do the biweekly project, we have to, I want to really set up the team. Like we have total 11. Higyu is teaching assistant. So I kind of insisted him to take the course, but with some reason he's not. He can't just take the class with the credit, so he's gonna just sit in and help me up. So we have 11 people. So I wanna make 3 as one group, even if it's a little bit too many. So this is the model, very important model, probability model, and log normal. Even if this log normal probability model, as I explained, very straightforward, believe it or not, if you're going to look at it, it's a little confusing. So as a next step, you can get your own data set, whether in your work or you can generate if you can, then fit this model how it fits, then tuned a little bit. And that's why I gave you all this by file. So this is the probability density function for log normal distribution, and this is cumulative distribution function. And as you see here, it has a skewness in there. So skewness in there, and as you see, skewness there. As you see here, this is if you look at, I'm going to draw the one here, which is this is a positive skew or negative skew? This is a positive or negative? It's a positive skew. Jungan said negative, right? Why? He didn't review yet because he was away for conference. That's perfectly fine. Higyu and Chorong are away to Lisbon to present a paper there. So this is a positive skew. In this case, this happened to be, I said over here, mu is equal to mu y. Okay. So this is a Wikipedia format, and our equation is notation is slightly different, and this guy is mu y happen to be 0, and sigma y happen to be 1. It just happened to be that, but you can change that. After you change this, of course you can plot the probability, log normal probability density function, no problem, you can fit in. To your data, you have to get the data. I'm not that nice person to give you the data, then just manipulate. You generate yourself. That way you can think more. How to get that? Where to get that? Did I generate the data set? Do I need to do some simulation work? Do I have to do some experiment in your area? Aline, you work with the 2 gentlemen, then you can join and get the... It's a different approach, a little bit annoying. But rather than giving you hard problems, screwed up, all that, then solve it. No. I want to generate, you can think. And this is depend on the parameter. When I say parameter, it has only two parameters, mu x, mu y, the mu x and sigma x. That's about all. Another parameter set, this probability density function goes like this. It has a variation. And this one is mu x is equal to still 0, and sigma y is equal to 0.25. Standard deviation is getting small, okay? Express the standard deviation in terms of the y, random variable. As you see, this is 1, this is 0.25. As it decreases the standard deviation, what do you notice here? P goes up, right? As sigma goes down, then dispersion is getting worse, simply speaking. That's what you see here. As the sigma y is larger, then uncertainty is larger. So if your data set is something like this, this may be the right choice to do. And others, as you see, depend on other. If you use other parameters, it can fit within that format. So this is the one probability model that I want you to exercise as a biweekly project. Biweekly project is not due this Friday, no, because you're gonna start this weekend. So I'm thinking about the around Monday, October 10 is a Monday. So you have a pretty good time. Then you can really turn in Monday. I think it's a Monday, right? Yeah, Monday. Turn in Monday then. Monday. So this is. I looked at the calendar the other day. It's a Monday. You can turn in. Okay. Then 3 of you work together. So I ask pick up the 2 probability model, 2 additional, as I mentioned the other day, just to pick out the 1 additional. So work out using 2 probability model. Data set is 1. Okay. 2 probability model, the log normal, then 1 additional. Poisson's, we're going to discuss the Friday. Poisson's models. You 3 of you can decide what model you will pick and go through the process to fit in to the probability model. Then you will use it as I going into the structure reliability calculation pretty soon. Okay, so that's the whole idea. I said, in addition to this, the last page you see the biweekly project assignment. I said solve example 2.7. I also indicate page number 35 through 36, precisely as shown in the problem set. Don't just look at solve, actually solve, turn in 2.7. All the basic informations are there. And use select the log normal and 1 additional probability model. Then select the data set in your area of interest. I don't select for you. When you conduct a thesis research, advisor is not going to conduct a thesis research for you. You have to sit down, you have to think a lot. Think a lot. If you don't think, then you lose. And fit your selected probability model to your data set. And after you put that in, then evaluate your probability model on how this will fit into your data. You have a feel, then evaluate. Okay? Then discuss parameter, how it characterizes the models and phenomena. Okay? Then depend on the selection of a probability model, then it's going to affect to the structure reliability value. Okay, I'll continue this tomorrow. Not tomorrow, Friday. Then at least this probability model you've got to finish by Friday. See, look at this. It's falling asleep. Believe it or not, that's what I'm. Huh? Yeah, that's no excuse. Okay, so I'll see you on Friday. I spend quite a bit on log normal distribution and use it. Okay? All right. I'll see you Friday.